So he's a PhD student in computer science at RTE. So that's the French TSO. Most of us, of course, know them very well. And he's also registered at the University of Paris Sud at the INRIA lab for research in computer science. And he has a strong interest in the energy domain and its environmental and societal implications, as well as in AI. And so I give you the floor, Balthazar.
Okay, thank you, Luis. So I will talk a little bit about graph neural solvers, which are a type of neural networks that were introduced for power flow computation. Okay, so as we said, I am a second-year PhD student at RTE and LRI, and my goal is to develop novel methods based on graph neural networks to optimize and control complex systems such as power systems. So in this presentation, I will try to answer three main questions. So first of all, what's a neural networks? Because we will need some of the basic equations to really understand the following. Then I will talk about graph neural networks, which are a quite novel approach to neural networks, and they are perfectly designed for data that have a graphical structure, which is indeed the case in power systems. And then I will introduce our main contribution, which we called graph neural solver. And then finally, of course, I will say a few words about the experiments that we conducted. So first of all, what's a neural network? So I'm pretty sure most of you already know some basics about it, but just to be sure, let's say that you want to learn a fast approximation of some function f that maps some vectors of dimension d in to vectors of dimension d out. So why would you need a fast approximation? Because in some cases, this function f can be pretty expensive to compute. So for instance, in the AC power flow problem, you need to solve a full optimization problem just to get the y that corresponds to a certain x. Okay, so we will use a neural network function, which we call nn of x. Okay, and the idea of neural networks is to compose very basic functions. So in this case, in this equation, we have a neural network that is said to have one hidden layer, and it is actually composed of three basic operations. So first of all, you have an affine transform, which means you multiply your input x by a matrix W1, and you add a bias B1. Okay, then you apply a nonlinearity, which can be, for instance, a hyperbolic tangent. And then finally, you apply another affine transform. And the whole idea of neural networks is that you will train and learn the parameters W1, D1, W2, and D2, so that your trained function will closely match your target function. So how do you do that? You need a data set, which is basically a set of pairs of x's and y's. So M here denotes the sample index. And indeed, you have to respect the following relationship between y and x, so that you have ym is equal to f of xm. And what you will do during training is that you will try to minimize the error, which is the mean distance between your predictions here and the ground truth here. Okay, and how do you do that? You do that by stochastic gradient descent method. And the whole what makes neural networks so attractive is that the gradient is actually very easy to compute thanks to the backpropagation algorithm. So you will perform a gradient descent in the space of the parameters of your neural network. Okay, so now let's try to apply this fancy neural network to a power flow prediction problem. Just to be clear, in everything that I will show on the slides, I consider the DC power flow prediction problem. But indeed, in all the experiments that we conducted, in everything that we've done so far, we consider the AC power flow problem. It's just for the sake of readability that I consider on the slides the DC problem. Okay, so as an input, you have the power productions and consumptions, which are the x's. So here your X has 4 dimensions because you have 4 electrical nodes. And using a solver, so whichever solver you want to use, for instance, Newton-Raphson in the case of the AC power flow problem, you can predict the voltage phase angle, for instance, here at every node. Okay, so now let's say that you use a lot of data to train your neural network. So you will basically have all the components of X vary sufficiently so that your neural network will see a wide variety of situations. And your neural network will actually get really, really good at predicting the voltage phase angle. But there is a big drawback to this naive approach, which is when you perform a permutation over the input data. So for instance, here at the top and the bottom, you have exactly the same power grid. There is just a simple permutation. So I permuted nodes 1 and 4 and nodes 2 and 3. Okay, so those two systems are exactly the same, but just permuted. But still, the physical laws are exactly the same. So if you use a solver, you will end up in both cases with exactly the same results. But you know, the bottom is a permutation of the top of the figure. So when you use your trained neural network, it will be really good in the setup that is described at the top of the figure, but it will be extremely bad for the permuted case because it has never seen this kind of setup. So it's actually a very, very, very big problem because regular neural networks are not permutation equivalent. So just a few words about this notion of permutation equivalence. Permutation equivalence means that if you perform a permutation over the inputs, it will result in a permutation over the outputs. So the AC power flow problem has this property. If you perform a permutation over the inputs, you should expect a permutation over the outputs. It's as simple as that. But still, we will still use neural networks as elementary learning blocks. So just keep in mind that neural networks are a set of parametric nonlinear functions that you can use to minimize, that you can train to minimize a certain objective. Okay, so now what's a graph neural network? So actually graph neural networks are quite recent class of neural network. They were first introduced in 2008, 2009, but they really gained in popularity around 2017. So it's quite a recent approach. And the overall idea is that it's an iterative process that relies on message passing. And the idea is that you will propagate information between direct neighbors of a graph. So considering the case that we had, that we've seen just before, here in this case, as an input, we need the injections, so power productions and consumption that are concatenated in X, but we also need information about the adjacency matrix. So for the sake of readability, I won't dive into detail, but indeed in all the experiments that we conducted, we include in A all physical information about the line, all physical characteristics. And what we will do is that we will create a latent representation of this graph. So we will associate to each node a certain variable that we call MI, which is a latent representation of the state of the node. And this information can be a vector of dimension D, where you get to choose the value of D. So if you want to include very large latent representation, you can. If you want to keep it scalar, you can also. So the first step is to initialize the latent representation. And at the very beginning, you initialize all the latent variables to 0, because at this point, you have no information over the neighborhood. So you cannot make any decision. And then you proceed to perform some sort of message passing. So here, I will detail this equation because it's very, very important to really understand this. So the idea is that you will update the message at node I by keeping the previous message, so mi at iteration k, plus a certain term that is a correction that depends on the local injection, xi, okay? And it also depends on the sum of over the neighbors, the direct neighbors of I, of a certain function of the messages of the neighbors. So the idea is that it's really important to take the sum here, because otherwise we would have a neural network that has an input that varies in size. So by taking the sum, we make sure that this term is always of the same size. Okay, and this function Lk and this function phi k are actually neural networks that we will learn, that we will train. Okay, and once you have propagated this information enough times, so big K times, where big K is also a hyperparameter of the architecture, then you decode your latent message that has no physical meaning into something that has a physical meaning, a physical unit, and that you try to in order to imitate the output of the Newton-Raphson method. So just to sum up the overall architecture, the first step consists in an empty initialization. So you associate to every latent message a 0 vector. Then you perform some message passing updates by keeping the previous message, but correcting it depending on the local injections and the information of the local, the direct neighbors. Okay, you do this message passing step big K times, and at the end, you decode it by applying another neural network, big D. And the idea is that D, Lk, and phi k will be trained jointly. So you will learn your full architecture at the same time. So graph neural networks are actually a class of neural networks that are permutation equivariant. So that means that if you perform a permutation over the inputs, it will mathematically result in a permutation over the outputs. The only drawback is that it requires the adjacency matrix. Another problem that we still need to face is that data can be expensive to generate in some cases. So that's why we've made this paper, this novel contribution, and that's why we introduce graph neural solvers. So if I describe succinctly the approach that we have developed so far, in order to train your graph neural solver, you need to sample a bunch of injections and a bunch of adjacency matrices. Okay, so you can sample them from your past, or you can also generate random situations, whatever. So once you've done this sampling step, you still need to compute the actual ground truth, so the Y star, which is obtained by minimizing the violation of Kirchhoff's law. So you basically solve an optimization problem using, for instance, the Newton-Raphson method. And then once you have obtained this ground truth, this Y star, you need to minimize the distance between your predictions and this actual ground truth. Okay. The problem is that the problem is this step number 2 because it requires you to solve a different optimization problem, and it's a bit heavy. So what we propose in this paper is to combine actually step 2 and step 3, and it's something that quite resembles something called physics-informed neural networks, because in the end, so we still have to sample X's and A's, so injections and adjacency matrices, but this time we will use as a training loss the violation of Kirchhoff's law. So this way, we do not need to call another solver to imitate. So it's no longer an imitation. It's really an optimization method by itself. So yes, it's a novel optimization that is based on graph neural networks, completely independent from any other solver, and we use physics violation as a training loss. So I will say a few words about the experiments. So what we considered are 4 standard I3E power grids, so with 9, 14, 30, and 118 nodes. And for each power grid, we consider the default situation that can be found in MATLAB. And we had added a lot of noise over both the injections and the line characteristics. And we also randomly disconnected some power lines to add some variety also on the adjacency matrix, so that you have a wide range of situations in all the 4 datasets. And indeed, in all 4 datasets, we splitted them into training and testing. And the idea is that we train our graph neural solver solely on the train part, and we test it on the test part. And then we compare it to the output of a Newton-Raphson method, which we consider to be the most trustworthy method. Okay. And so here we have a plot of the correlations between graph neural solvers and the Newton-Raphson method. So just consider the top row. You can see that in all 4 cases, we managed to have a very strong correlation with the Newton-Raphson method, even though we are not imitating the Newton-Raphson method. Keep in mind that the graph neural solver was trained without any information about the Newton-Raphson method. But we still managed to have a pretty decent correlation, even though we can see that the larger the grid, the lower the correlation. So that's definitely something that we need to improve and work on to ensure scalability of such approaches. At the bottom of the figure, you can see the correlation between the DC approximation and the Newton-Raphson method. The DC approximation relies on linearization of the physical equations, and you can see that it performs much worse than our graph neural solver. Okay, now in terms of computational time, so in this picture, we showed the results for the different experiments. On the x-axis, you have the computational time, so the seconds per power flow, and on the y-axis, you have the percentage of error compared to Newton-Raphson. So indeed, Newton-Raphson is at 0 because we believe it to be the most trustworthy method. But we can see that our proposed graph neural solver for all 4 experiments, so here 9 nodes, 14, 30, and 118 nodes, we managed to beat the DC approximation, both in terms of error and computational time. And indeed, compared to the Newton-Raphson method, our proposed graph neural solver is 1 to 2 orders of magnitude better. So what we introduced so far is really a novel optimization method that is very different in nature from classical optimization. It's completely independent from other methods and based on graph neural networks. We experimentally obtained high correlations with Newton-Raphson method while obtaining some important gains in terms of computational time. So in a recent work that we just submitted to another conference, we tried to improve on the theoretical foundations and tried also on to assess this approach on different problems. Finally, for future work, we would like to address different problems stemming from optimization, such as ACOPF, voltage control, and topology optimization. If you want to take a look at the code, you can check my GitHub. So the code is a bit messy, not maintained, but I believe that it could still be useful for some of you. And indeed, if you have any questions, feel free to contact me. But I am currently working on a cleaner and more user-friendly version of this work that could be used for problems different from the, from the AC power flow problem. So thanks a lot for your attention. And if you have any questions.
Thank you, Balthazar. This was, I think, a very interesting presentation. And the people were really listening to you until the very last minute. So we have only 3 questions.
Okay.
Maybe there will others will come up, but so the first one is the initial latent representation.
Yeah.
You said it's initialized with zeros. And so the question is the initial latent representation also learned during training?
No. Actually, that's a choice that you need to make. And when it comes to graph neural networks, there are many ways of doing exactly the same thing. So in my implementation, I chose to consider always a zero initialization. And then by performing the message passing steps, indeed, those messages will be updated. But it's really a choice that you have to make, and I chose a full zero.
So maybe I may complement this, because my question I had is that, okay, let's say the AC power flow may have multiple solutions, right?
Mm-hmm.
And so even if you formulate it as you have formulated it, you can have several solutions. And so how do you make sure somehow that you are converging, let's say, to the regular solution, which is usually obtained when we use a flat start in the AC power flow?
That's a very good question. That's something that we definitely need to improve, because so far we have observed that we obtained the same results as the Newton-Raphson method, but we have no guarantee over which solution we found, and that's actually a big drawback of this approach.
Okay, thank you. So okay, and then I have a question. Okay, questions are coming in, so it's
that's a lot.
It's a rush of questions now. Suddenly we have 10. Wow, I don't know how to select this, but maybe one question from Simon Tindemans. Says, your method seems to generalize well across networks. The solver trained on the largest network has the best performance across all networks. Figure 9 in the paper, so we read the paper. Can you hypothesize whether training on an infinitely large network will lead to asymptotically perfect performance, given enough training data?
That's a good question. In the AC power flow problem, you will encounter a very important problem. The problem is that you cannot perform an AC power flow on an infinitely large power grid, because when it comes to the voltage phase angle, it's really something that needs to take into account the full grid. It's not a very local information. The theta is a global information, so you really need to have to gather information from all the grid. And actually, in some recent results, we showed that the relevant metric for how many times you need to propagate the information is actually the diameter of the graph. Because, and it's actually quite easy to understand, because to make a good prediction for each node needs to have gathered the information from all the grid. So that's why you need to have at least a number of propagations that is at least the diameter of the graph. So maybe it doesn't completely answer your question, but basically you cannot work on infinitely large.
In some sense.
Yeah.
Okay, this is good. Now there is a last, I guess you can quickly answer to that one. It's about somebody who is familiar of your work and of the work of your team. Is about super generalization capability, meaning you can generalize over topologies, I guess.
Exactly. So this was not the point of this paper, because we wanted to include the varying line characteristics in this paper. We wanted to accelerate the computations, but in some previous work that you can find in the reference of the paper, we managed to show that by training on random power grids of 30 nodes, you manage to have a very good accuracy also on power grids of 110 nodes. So that means that you have trained your graph neural solver on a quite small power grid, and you still manage to generalize to very different and much larger power grids. Okay. So those are experiments from another paper.
Unfortunately, for the sake of time, we have to cut these presentations, and we don't have the coffee break possibilities of, let's say, physical meetings of PSCC, where certainly many people would have come to talk with you about your work, but maybe, let's say in the future, some kind of other webinar about this kind of work will be organized.